You've been working so hard. You wrote all those lines of code and delivered the app before the deadline. Then your boss comes and says, "Hey, we need to track when each function runs for auditing. I need you to modify the hundreds of functions that are in this app." Begrudgingly, you open the code editor to make the same change to each function. Or will you? Python decorators. They allow you to modify multiple functions without repeating yourself. Today we'll see how decorators work, and we'll build our own decorators to keep things dry. Let's begin. Let's jump straight to an example. Here's a function called myfunc. It does something basic, just prints hello world. Here's another function called myDecorator. We'll get to that in a little bit. Placing decorator above myfunc changes how myfunc runs. This @ symbol says that we want to modify the function below, myfunc, with myDecorator. If we redefine myfunc with the decorator and run again, we'll see that the output's a little bit different. By itself, myfunc just prints hello world, but when it's decorated, we see we have a few more print statements. But how does that work? That @ symbol performs some reassignment. When Python sees the @ symbol, it assumes that whatever comes afterward is something that can take a function as an input and return a function. Whatever is returned from the decorator is reassigned to the name myfunc. That's a little complicated, but it makes more sense if we decorate functions manually. Here we have the same function without the decorator above, and we are explicitly passing that function to the decorator. Remember, a decorator must receive a function as its first argument. Whatever is returned from myDecorator is then reassigned to that same name, myfunc. But this is a little messy. We can see we're using the myfunc name a couple of times, so it's more common to use the compact decorator syntax. It does the same thing as the manual decoration that we saw before. So what is myDecorator doing? Well, it takes the input function, aliased as func, and in the function body it does two things. It defines an inner function wrapper, and then it returns wrapper. This wrapper that's returned is what is reassigned to the name of the original function, myfunc. Within the body of wrapper, we have a print statement, we run the original function, and another print statement. That's why when we ran myfunc a second time, we were really running an instance of this wrapper function. Specifically, this print statement gives us before function call, running the original function gives us hello world, and then the last print statement gives us after function call. And that's it. That's all a decorator does. It extends or modifies the behavior of your original function. Decorators are amazing, and they're used all over the Python ecosystem. Here are some common cases of where you might find decorators. You can use decorators to register functions in your app objects. Think of those times that you were using Flask or Fast API and used a decorator to let the app know what function maps to what route. You can also use decorators to measure the time performance of your functions. Use decorators to restrict function calls to users with particular permissions. Decorators can emit logs each time functions are called, kind of like what your boss asked you to do. You can filter the inputs and outputs of functions. You can cache the output of a function for reuse. You can limit how often functions are called. You can even pay your taxes. Kidding about that last one. The point is, decorators can be used for many things. You're limited only by your imagination. To jog your imagination, we'll look at some exciting examples. Back to the terminal. This first example was kind of boring because it received no arguments. Let's look at an example of passing arguments to a decorator. Here's another decorator called yell. It receives func as a parameter. It defines an inner function called wrapper, and then it returns that wrapper. That's what decorators do. This time you'll notice though that wrapper has variable parameters. It has *args and *quargs to capture any number of arguments. If you're not familiar with variable parameters, check out this video on Python function parameters. You'll often see *args and *quargs in the definitions of decorators, and that allows the decorator to be applied to many different functions. In the body of wrapper, we see that *args and *quargs is being unpacked and passed to that original function. The result is stored in a variable called result, and assuming that the variable is a string, it is uppercased when it's returned. Let's see it in action. Here we have a function called castSpell, and we'll first run it without the decorator. Running it, we get raising wand expecto patronum. Now, let's define our decorator, apply it to our function, and run the function again. And we can see we get the output in uppercase with some exclamation marks at the end. Cool, we just modified the existing function. Instead of writing the uppercase logic within the original function, we got the same effect with this yell decorator. This means we can reuse the modification for another function. Here's a function called purchaseBroom, and we can see that it returns a string as well. If we put the decorator on top and run the function again, we get the same modification as before without having to change the original function. Now for the bad news. In all this excitement, we lost something. Without the decorator, purchaseBroom had some important information. We could see some metadata about the function. For example, we could see that purchaseBroom points to this object in memory. We could also see the documentation of purchaseBroom and the annotations associated with it. But when we use a decorator, we see that that information is lost. This time, the name purchaseBroom points to this internal wrapper object. The documentation is gone, and so are the annotations. This is not good when you're knee-deep in a debug session and you're trying to figure out what your code is doing. We need this metadata to know where we are in the code and what the code is doing. If only there was a way to decorate a function and keep the original metadata. And there is, with yet another decorator. In the standard library, there's a package called functools, and in functools, there's a decorator called wraps. The sole purpose of wraps is to make the decorated function look like the original function. Here we'll import wraps from functools, and we'll just make one change to our original yell decorator. We'll add this line right above the wrapper, which decorates wrapper. This will effectively tell Python that, hey, I want to make this wrapper look like the original function, or func, that was passed into the decorator. So we'll redefine yell, and we'll redecorate our purchaseBroom function. And this time, if we inspect the object, we can see that we still have access. We still have access to the original metadata. purchaseBroom still points to a function object that is named purchaseBroom. The annotations in the doc string are still present. Excellent. This first example shows how we can pass arguments to a decorated function and how we can retain metadata. Now let's look at a decorator that does some work before and after the function call. Here we have a decorator called TikTok. No, not the social platform that's rotting your brain. Let's see what TikTok does. As always, it defines a wrapper function and returns that wrapper function. And at some point, the original function is being called and stored as a result. But right before that function is called, we use time.perfCounter to log the start time. And right after the function call, we call time.perfCounter again to log the end time. And just before the result is returned, we print something. We print the difference between the end and start time to show how long the function took to run. We also, within this f string, call out the function's metadata to print the function's name. Let's try it out. Here we have a problematic function called troublesome function. If we decorate it with TikTok, we should be able to see how long it takes the function to run. We'll define it, and then calling that function will wait a little bit, and we'll see that this function took about 3 seconds. Again, the original function ran first, and we got the output from the original function, and then we can see the whole thing took about 3 seconds. Again, this shows how a decorator can be used to perform some work around the original function. When you're debugging, you can apply this TikTok decorator to the top of any functions to figure out which ones are taking too long. Next example. Suppose you need to keep track of when your function runs, maybe to make sure that you don't run it too frequently. We'll build a decorator that logs when our function last ran, and if it's been less than 10 seconds since the last call, the function will not run. This one is a little more complicated, so we'll build slowly. We'll build a decorator called rateLimit. Since it's a decorator, rateLimit will take a function, func, define an internal function called wrapper, and then return that wrapper. At the very least, wrapper needs to take some number of arguments, call the original function, and then return that function. This is the minimum needed for a decorator. It does not extend the functionality, but it does work. Now, how would we stop this function from running if it's been less than 10 seconds since the last run? In an ideal world, we'll have two variables, now and last called, that track time. Now might represent the current time, and last called might represent the time that the function was last called. If the difference between these two is less than 10 seconds, then we can raise an exception and stop the rest of the function from running, meaning that we never get to this line where the original function is called. But if it has been more than 10 seconds, then we do reach this line and the function is allowed to run again. Getting the current time is easy. We can import time and use time.time to log the current time. But what about last called? Well, the naive approach is to define last called at the beginning of wrapper and initialize it to 0. If the time difference check passes, we can update last called to be the current time for the next time that the function is called. But this wouldn't quite work. Because every time wrapper runs, we would reset last called to be 0. And even after wrapper runs, last called would cease to exist. Everything in a function body ceases to exist after the function runs. So how can this inner function wrapper maintain state or keep track of last called? The answer is closures. Since wrapper is an inner function returned by this outer function, we can move anything we want to keep track of into wrapper's enclosing scope. That means we can move last called from the body of wrapper to the body of rate limit. Now, when wrapper is returned, it is effectively bundled up with last called and still has access to last called even after the rate limit function has run. Since we're assigning a new value to last called in the body of wrapper, we'll need to use the non-local keyword. This tells Python that last called is in the enclosing scope and not supposed to be a local variable. If this talk of closures and enclosing scope and non-local keyword doesn't make sense, check out this video on Python scope. Will it work? Let's see. Here's the decorator we defined in the slides, and here's a function that simulates calling an API. Maybe it's an API that throttles our usage if we call it too often. And to make sure we don't break the API's rules, we'll decorate our API function with rate limit. This means that if we call the function the first time, it should run. Trying to call the function again within 10 seconds fails. But if we wait a little bit, the function is allowed to run again. Cool. This is an example of how you can use closures to manage state when you're decorating your functions. We can go on and on with examples, but we'll wrap up here. Remember, a decorator is a function that calls a function and returns a function, potentially extending its behavior along the way. Well, I kind of lied. Our conversation has talked about functions, but technically, decorators apply to any callable. Here's the true definition. A decorator is a callable that takes another callable and returns a callable. This means that decorators can decorate a class, or they can be a class. We've just scratched the surface of what we can do with decorators. I hope this motivates you to use decorators or design your own in Python. If you want more examples of decorators, check out the blog linked in the description below. Spoiler alert, there's an example of a parameterized decorator that requires a function within another function. That's right, 3 levels deep. What are some ways that you use decorators? Let me know in the comments below. And if you like what you see, please like and subscribe. Until next time, happy coding.